close your eyes and feel the gentle pulse of this moment. But what if I told you that the very tick you just experienced never truly happened at all? Tonight, we drift into the gossamer realm, where Einstein's universe whispers its most profound secret, that past, present, and future are nothing more than stubborn illusions dancing in the theatre of your mind. As your breathing slows and consciousness softens, prepare to discover why the river of time you've always trusted may not be flowing at all. What does a beginning look like when there is no before to compare it with? Could silence be the first chapter of creation, an unlit stage where law, distance, and duration have not yet learned their names? In that primal instant, the cosmos arrived not as an explosion into space, but as space coming into being. Time, energy, and the rules that would govern them emerged together, braided like threads of one newborn fabric. Expansion outran comprehension. The metric itself swelled, carrying every point away from every other, not by motion through a pre-existing void, but by the void learning to widen. Temperatures towered beyond any star's core, and matter, still nameless, flickered as fields and quanta struggled for identity. A brief, decisive bloom, often called inflation, smoothed the young universe while magnifying the tiniest quantum tremors. Those minute ripples, barely 1 part in 100,000, became the seeds of structure. They were not imprinted by a hand, but by statistics. A restless foam stretched across an expanding stage. After inflation eased, the fabric kept growing, slower now, and the frozen tremors remained like faint initials pressed into cooling clay. As cooling progressed, unity fractured into distinct forces. Gravity kept its long reach, curving the stage itself. The strong interaction learned to bind quarks into protons and neutrons. The electroweak symmetry parted, leaving electromagnetism to guide light and chemistry, while the weak force governed subtle transformations. In that furnace, most matter met antimatter and vanished in floods of radiation, yet a slight imbalance, perhaps 1 particle in a billion, left a surplus. That quiet excess would become everything: gas, rock, sea, cloud, and mind. The cosmos wrote its first durable nouns in minutes. In a process called primordial nuclear synthesis, protons and neutrons coupled into light nuclei, hydrogen in abundance, helium by the handfuls, with traces of deuterium and lithium. Neutrinos, almost indifferent to matter, streamed free as silent witnesses, carrying away a record of densities and heat. The universe remained opaque then. Photons ricocheted in a dense fog, forever scattered, unable to travel far without being turned aside. Hundreds of thousands of years later, the fog thinned. As expansion cooled the sea of particles, electrons settled into orbit around those light nuclei, and neutral atoms formed. With scattering suddenly rare, light could, at last, voyage in straight lines. That first free radiation still arrives from all directions as a gentle glow, the cosmic microwave background, its spectrum near perfect, its temperature just above absolute zero. It is a map of the infant universe, a portrait painted when darkness first learned to be transparent. In that soft afterglow rests a clock older than any calendar. Its subtle mottling tells of the original ripples, their sizes and strengths, the amount of ordinary matter, dark matter, and the curve of the stage itself. Each photon is a courier from an era before stars, carrying the memory of a universe that was simple, hot, and nearly uniform. From those nearly even beginnings, gravity would amplify the tiny differences, gathering gas into threads and nodes, drawing the future shapes of galaxies from statistical whispers. With structure's promise came direction. The arrow of time is not imposed by decree but invited by conditions, a low-entropy youth rolling toward complexity. As the cosmos fell from hot uniformity to colder, clumpier variety, processes learned to prefer one order over another, ashes after fire, waves after wind, fossils after life. Time, once indistinguishable from creation's turmoil, found orientation in the gentle tilt from smooth to structured, from potential to history. This is the whisper before time learned to speak fluently. a stage assembled, a script of laws composed, and a faint chorus of ancient lights still singing across the dark. In that chorus, beginnings are measurable. The hiss of the microwave background is not noise but memory, a lullaby from the first clear night, counting the seconds since the fog lifted and reminding each new star that it was born from ripples small enough to hide in a grain of sand. Creation's first act smoothed its own canvas, then seeded it with the faintest imperfections, tiny variations that would become the scaffolding of everything large. Space did not expand into emptiness. Emptiness learned to widen, carrying every point away from every other. In that swift opening, roughness was ironed flat, and quantum jitters were magnified from subatomic murmurs into cosmological blueprints. The stage was set not by explosion, but by stretching, a bloom so brief and decisive that it reset the geometry of the newborn cosmos. Inflation's surge subsided, and cooling began its careful work. Symmetries gave way in sequence, the electro-weak unity split, electromagnetism and the weak force taking separate roles. The strong interaction bound quarks into protons and neutrons. Gravity continued as quiet architect, curving the arena itself. Matter and antimatter largely annihilated into radiation, yet a delicate excess of matter endured, about 1 part in a billion, leaving the raw stock for stars, planets, and later minds. The young universe was a bright plasma where photons bounced from charged particles, turning matter and light into a single ringing medium. Pressure waves rippled through this glow like sound in a cosmic instrument. Dark matter, untouched by electromagnetism, slipped free of the photon drag and gathered first, pooling into invisible halos that would later cradle galaxies. Ordinary baryons felt both the pull of gravity and the push of light, carving acoustic peaks whose preferred spacing still echoes in the large-scale pattern of galaxies. Minutes after the beginning, primordial nuclear synthesis fused protons and neutrons into light nuclei, mostly hydrogen, a generous share of helium, and traces of deuterium and lithium. The universe remained opaque until expansion cooled it enough for electrons to settle into orbits around those nuclei. With recombination complete, the fog thinned and photons could finally travel unimpeded. That first free light survives as the cosmic microwave background, a nearly perfect blackbody now chilled to about 2.7 Kelvin, mottled by mere tens of microkelvin. Its subtle pattern encodes the contents, curvature, and age of the whole, a fossil photograph of the moment transparency began. A long twilight followed, often called the Dark Ages. Gas drifted into dark matter halos and cooled, densities deepening the dimples left by inflation. When the first metal-free stars ignited, massive and short-lived, the universe's darkness fractured. Their ultraviolet radiation rionized the intergalactic medium, carving expanding bubbles of transparency until neutral hydrogen gave way to a clear, star-laced sky. The great quiet ended with a patient chorus of light. Those pioneer stars forged new possibilities. In their cores, fusion stepped beyond hydrogen and helium to carbon, oxygen, and heavier elements. In death, supernovae scattered these seeds into surrounding gas. Dust condensed, chemistry diversified, and later generations of stars formed with planets in tow. Complexity rose not by miracle, but by cycles. Clouds into stars, stars into elements, elements into worlds. Galaxies assembled along filaments of the cosmic web, spirals and ellipticals growing through accretion and mergers. Supermassive black holes kindled at their centers, shaping their hosts with winds and jets. Across all scales, expansion continued, stretching wavelengths and cooling backgrounds, while gravity collected matter into luminous architecture. The unfolding did more than occur in time. It defined time's practical meaning for matter and light, translating a low entropy opening into a hierarchy of structure. Here the arrow of time found traction. Energy cascaded from concentrated forms to diffuse warmth. Entropy climbed and records accumulated in spectra, in dust, in the faint hiss of ancient radiation. Each epoch, recombination, rionization, galaxy formation, became a verse in a patient chronicle, legible in photons crossing an ever-growing sea. From a smoothed canvas and whisper-small ripples, The universe learned to write in stars. Gravity is a shape rather than a shove. The stage dissolves into fabric, and the fabric learns to curve. Space and time, once imagined as separate halls, braid into a single cloth where intervals replace absolutes and simultaneity loosens its grip. In this softened geometry, every particle, planet, and beam of light traces a thread, its world line, through a living tapestry whose weave changes as energy flows. The clue is simple and profound. In a freely falling elevator, weight vanishes. Acceleration and gravity become indistinguishable in a small enough region, revealing that what feels like a force is often geometry doing its quiet work. This equivalence principle guides the leap from force to curvature. Straight lines become geodesics, the straightest possible paths permitted by the fabric, so free fall is not a tug but a surrender to the contour of space-time. Light fixes the boundary all observers share. Its speed remains constant, not because clocks conspire, but because the metric insists. From that constancy arise light cones, elegant funnels that parcel events into can influence, can be influenced, and forever separate. Causality is sketched in these cones. Tilt them by motion or bend them with mass, and the map of possible stories changes, though never in a way that lets effects outrun their causes. Time itself thickens or thins with circumstance. Near deep gravity, clocks slow. On swift trajectories they hesitate. The difference is small atop a mountain and dramatic beside a neutron star, yet the rule is the same. Geometry sculpts duration. Rulers answer as well, shortening along directions of motion so that the speed of light stays inviolate and the accounting of events remains consistent for all who measure. These subtleties are not confined to thought. Navigation satellites carry disciplined clocks that drift in orbit, unless corrected for both their speed and their altitude in Earth's gravitational well. Muons born in the upper atmosphere survive to sea level because their internal ticking lingers in flight. Laboratory clocks sense a change in rate between floors of a building, turning architecture into a gentle observatory of curvature. Matter tells the fabric how to bend, and the fabric tells matter how to move. Starlight detours around suns. Clusters of galaxies magnify and shear the glow behind them, painting arcs and rings on the sky. Gravitational lensing exposes invisible scaffolding, letting dark matter be mapped by the way it shapes the paths of photons. A distant quasar, seen in several places at once, becomes a mirrored note sustained by geometry. Curvature can travel. When massive bodies whirl and merge, they ring space-time like a struck bell, sending ripples outward, gravitational waves that lengthen and shorten space by less than the width of a proton across kilometers of baseline. Detectors listen with laser stillness as two black holes fold into one, the waveform recounting masses, spins, and distances. It is sound without air, rhythm written directly in the metric. Where curvature steepens, horizons appear. Near a black hole, light can orbit in a precarious circle before choosing escape or surrender. Signals climbing from that depth arrive redder, and later, a delay called the Shapiro time lag, while clocks stationed too near would seem to stall to far-off eyes. None of this requires a push. The script is written in slopes and wells that world lines cannot help but follow. On the largest scales, the geometry itself expands. Distances grow not because galaxies race through space, but because space between them lengthens. Ancient light stretches into longer colors, and the cosmic microwave background cools as the metric swells. Even here, light cones keep order, and the same rules that guide an apple's fall govern the drift of superclusters along the filaments of the cosmic web. Thus the cosmos resembles a loom at work. Energy and momentum act as shuttles, weaving curvature into pattern. World lines thread through the result. Clocks and rulers, humble tools, read back the design. Time is not merely counted, but shaped, retarded in valleys of gravity and hurried on plateaus of motion. In this script, geometry instructs and matter obeys, while matter, in turn, revises the script, an endless, elegant negotiation that writes the history of everything that moves. Light keeps a single promise. In empty space, its pace never changes. That constancy is the quiet hinge on which modern physics turns. Clocks and rulers must bend to honour it, so time can dilate and lengths can contract just enough to keep cause ahead of effect. Simultaneity loses its universal crown. What lines up in one frame may stagger in another. The geometry of influence is drawn as light cones, narrow toward the past and wide toward the future, dividing events into those that can touch those that can be touched, and those forever beyond reach. In this covenant, photons do not feel the passage of time. They trace null geodesics, the straightest possible paths permitted by curved spacetime. Around stars and galaxies, those paths deflect, not because light slows, but because the fabric itself is bent. A beam grazing a massive body arrives late and redder, delayed by the depth it climbs from. Near a black hole, a precarious orbit of light circles at the photon sphere, while deeper still a horizon ends every outward journey. Curvature writes detours. Light reads them faithfully. Though glass and gas can tame its speed, the vacuum leaves light unbound by dispersion. What changes instead is colour. Motion shifts wavelength through the Doppler effect. Gravity shifts it through redshift or blueshift, trading energy with the climb. The spectrum of a star lined with dark notches from specific atoms becomes a ledger that records motion, depth, and temperature all at once. In its fine structure, a story is told without a single spoken word. Across intergalactic reaches, expansion performs a different transformation. Space itself lengthens, wavelengths stretch with it. Ancient photons depart in visible or ultraviolet hues and arrive as microwaves, cooled by the swelling of the metric. The glare of the early universe has drifted down to a 2.7 Kelvin murmur, the cosmic microwave background, its nearly perfect blackbody curve punctuated by microkelvin ripples. That faint hiss is a rolling chronicle, measuring age, content, and geometry with the patience of cooling light. Redshift also marks the recession of galaxies. Spectral lines slide to longer wavelengths in proportion to distance for faraway systems, revealing the Hubble-Lemaitre expansion. Standard candles such as Type Ia supernovae calibrate the scale, while standard rulers like baryon acoustic oscillations mark preferred separations imprinted in the early plasma. Time delays between multiple images of a lensed quasar add another yardstick, turning gravity's mirroring into a cosmic clock. Each technique treats light as both messenger and meter. Finite speed transforms the sky into an archive. The sun's face is seen 8 minutes in the past. The nearest big galaxy appears as it was millions of years ago. Deep fields capture galaxies whose light began when heavy elements were scarce and stars were young. Observation is always remembrance. Even the cosmic horizon, the farthest boundary from which light could ever have reached, moves as the universe ages, setting a limit on what can be known but not on what can be imagined. Gravitational lensing sharpens this archive into relief. Clusters bend background light into arcs and rings, magnifying what would otherwise be invisible. By mapping those distortions, the dark scaffolding of the cosmos emerges, traced by light that cannot feel the dark but must follow its curves. A distant supernova multiply imaged by a lens can reappear years later in a different arc, its timing predicted by the path lengths that geometry demands. The same covenant binds ripples in spacetime itself. Gravitational waves, moving at light speed, carry timings of cataclysmic mergers across the abyss. When their arrival coincides with a flash of electromagnetic light, distance and expansion can be cross-checked by two messengers speaking the same tempo. The universe keeps time without a master clock, by comparing rhythms carried on different paths through the same elastic stage. Thus, light sketches a chronology without decree. Constancy preserves causality. Curvature sculpts roots. Motion and expansion tint the spectrum with meaning. In reading those tints and delays, ages and distances unfold. The cosmos offers no central metronome, only a covenant honoured everywhere. One speed in vacuum, and a patient ledger written in colour, angle, and arrival time. From that ledger, a universe grows legible, one photon at a time. Time gathers in valleys and thins on heights. Where gravity is deep, moments arrive reluctantly. Where gravity is gentle, they pass with a lighter step. This contouring of duration gives the cosmos an hourglass texture, sands of time pooling in wells, flowing more freely across plateaus. The effect is not metaphor alone, but measurement. Clocks reveal it with quiet certainty. The rule begins with curvature. Mass and energy bend spacetime, and that bending changes the rate at which intervals unfold. A clock placed high on a mountain gains a whisper of pace compared with one kept at the shore. Carry the same clock toward a neutron star, and its seconds stretch long, drawn out by gravity's depth until time itself seems to hesitate. Gravitational potential becomes a dial, and time's hand turns faster or slower depending on altitude in that field. Light confirms the gradient. Climbing from a well, a photon loses energy and reddens. Falling inward, it is blue shifted. This gravitational redshift links color to potential and duration to depth. Radio signals sent past a massive body return late, the Shapiro delay, because the curved path is longer in spacetime than straight intuition suggests. Even the orbits of planets whisper the story. Perihelion precession, minute but steady, marks the difference between Newton's pull and geometry's guidance. The principle is at work in ordinary technology. Navigation satellites circle Earth with atomic clocks that tick in weaker gravity and at high speed. Motion slows them, altitude speeds them. The net result requires daily corrections, so positions on the ground remain faithful. Laboratory clocks have become so precise that a change of mere centimeters in height produces a measurable difference in rate. Timekeeping has turned into cartography. Chronometric geodesy maps the geoid by listening to time's pace. Experiments have traced this hourglass for decades. Photons shifted in frequency over the height of a tower. Airborne clocks flown east and west returned with different totals. Optical lattice clocks now compare floors in a building and find the expected disparity. Each test translates theory into rhythm, showing that time is not absolute flow but local tempo, set by the shape of the arena. On cosmic scales, the contours deepen. A cluster of galaxies carves a broad dimple into space-time, magnifying background galaxies into arcs and rings. Light taking different routes around the cluster arrives at staggered times. A single supernova can appear, fade, and reappear in a mirrored image years later. These delays are not accidents but signatures, timing marks that let mass distributions be weighed in units of seconds. Near horizons, the hourglass narrows to a throat. Close to a black hole, a distant observer sees infalling clocks slow toward a standstill, their signals dimming and redshifting into silence. At the photon sphere, light itself can orbit, balanced between escape and surrender. Time there is stretched so thin that minutes far away correspond to long, reluctant beats in the depth. The same contouring shapes temperature and age. Background radiation cools as the universe expands, but passing through wells adds tiny anisotropies, integrated Sachs-Wolf traces, where gravity's evolving grip lends or takes energy from ancient light. In the web of large-scale structure, potential wells and hills modulate not only motion, but the bookkeeping of when events occur and how they are seen. Thus, time's texture is not uniform fabric but relief map. Geometry sets the contours, matter sculpts the basins, and clocks read the terrain. From mountain observatories to satellite constellations, from galactic lenses to the brink of horizons, one story repeats in different keys. Matter warps the arena guides matter, and in the margins of every signal, a clock quietly tells the tale of gravity's hourglass. Time gathers in valleys and thins on heights. Where gravity is deep, moments arrive reluctantly. Where gravity is gentle, they pass with a lighter step. This contouring of duration gives the cosmos an hourglass texture. Sands of time pooling in wells, flowing more freely across plateaus. The effect is not metaphor alone, but measurement. Clocks reveal it with quiet certainty. The rule begins with curvature. Mass and energy bend space-time, and that bending changes the rate at which intervals unfold. A clock placed high on a mountain gains a whisper of pace compared with one kept at the shore. Carry the same clock toward a neutron star, and its seconds stretch long, drawn out by gravity's depth until time itself seems to hesitate. Gravitational potential becomes a dial, and time's hand turns faster or slower, depending on altitude in that field. Light confirms the gradient. Climbing from a well, a photon loses energy and reddens. Falling inward, it is blue-shifted. This gravitational redshift links color to potential and duration to depth. Radio signals sent past a massive body return late, the Shapiro delay, because the curved path is longer in spacetime than straight intuition suggests. Even the orbits of planets whisper the story. Perihelion precession, minute but steady, marks the difference between Newton's pull and geometry's guidance. The principle is at work in ordinary technology. Navigation satellites circle Earth with atomic clocks that tick in weaker gravity and at high speed. Motion slows them, altitude speeds them. The net result requires daily corrections, so positions on the ground remain faithful. Laboratory clocks have become so precise that a change of mere centimeters in height produces a measurable difference in rate. Timekeeping has turned into cartography. Chronometric geodesy maps the geoid by listening to time's pace. Experiments have traced this hourglass for decades. Photons shifted in frequency over the height of a tower. Airborne clocks flown east and west returned with different totals. Optical lattice clocks now compare floors in a building and find the expected disparity. Each test translates theory into rhythm, showing that time is not absolute flow but local tempo set by the shape of the arena. On cosmic scales, the contours deepen. A cluster of galaxies carves a broad dimple into space-time, magnifying background galaxies into arcs and rings. Light, taking different routes around the cluster, arrives at staggered times. A single supernova can appear, fade, and reappear in a mirrored image years later. These delays are not accidents, but signatures, timing marks that let mass distributions be weighed in units of seconds. Near horizons, the hourglass narrows to a throat. Close to a black hole, a distant observer sees infalling clocks slow toward a standstill, their signals dimming and redshifting into silence. At the photon sphere, light itself can orbit, balanced between escape and surrender. Time there is stretched so thin that minutes far away correspond to long, reluctant beats in the depth. The same contouring shapes, temperature and age. Background radiation cools as the universe expands, but passing through wells adds tiny anisotropies, integrated Sachs-Wolf traces, where gravity's evolving grip lends or takes energy from ancient light. In the web of large-scale structure, potential wells and hills modulate not only motion, but the bookkeeping of when events occur and how they are seen. Thus, time's texture is not uniform fabric, but relief map. Geometry sets the contours, matter sculpts the basins, and clocks read the terrain. From mountain observatories to satellite constellations, from galactic lenses to the brink of horizons, one story repeats in different keys. Matter warps the arena. The arena guides matter, and in the margins of every signal, a clock quietly tells the tale of gravity's hourglass. Time leaves fingerprints, matter keeps them. In wood grain and glacier glass, in coral bands and crater rims, the past settles into patterns that can be read long after the moment has gone. Records bind moments to matter, turning passing weather into rings, passing seasons into layers, and passing light into spectra. The world becomes an archive, each shelf built by physics and chemistry, each page written in structure and stain. Trees tally years with alternating bands of fast spring growth and dense latewood. Dry summers squeeze the rings thin, wet years widen them. A forest becomes a ledger of droughts and deluges, cross-dated across valleys to reconstruct centuries of climate. Far to the poles, snowfall compresses into annual sheets of ice. Trapped in those layers are bubbles of ancient air, tiny ampules of atmosphere that preserve bygone concentrations of carbon dioxide, methane, and volcanic ash. Drilled and lifted to daylight, an ice core whispers the cadence of ice ages and interglacials with the steadiness of a metronome buried in snow. Lakes keep time in varves, light and dark laminations laid down year by year as spring floods and winter calms alternate. On seafloors, sediments accumulate chemical traces of temperature and productivity, ratios of oxygen 18 to oxygen 16 in shells from long-dead plankton shift, with the warmth of the water in which they grew. In cooling lava, iron-bearing minerals align with Earth's magnetic field, freezing compass needles into stone. Bands on the ocean floor record reversals of the field like barcodes, a moving tape that dates the opening of basins and the drift of continents. The heavens keep ledgers of their own. Starlight is stamped with spectral lines, the fingerprints of elements. Their positions and shapes reveal temperature, pressure, rotation and motion along the line of sight. Pulsating stars keep precise rhythms. Clusters display color magnitude patterns that age like faces, allowing entire families of stars to be dated at a glance. White dwarfs, the embers of sun-like stars, cool in predictable arcs. A population of such embers forms a cooling sequence, a cosmic thermometer turned into a clock that times the histories of clusters and the disk of the Milky Way. Information is the art of arranging matter so that one pattern can stand for another. DNA encodes ancestry and adaptation in a 4-letter scripture wound into every cell nucleus. A single mutation, a duplication, or a shuffled segment becomes a note in the long song of descent, and comparative genomics turns those notes into timelines. Epigenetic marks, methyl groups, histone modifications layer recent experience on older text, a penciled margin that can fade or persist across generations. In rock, isotope ratios tally radioactive decay. In the brain, changing synaptic strengths and new connections stabilize a moment into memory. Thermodynamics charges a fee for all of this bookkeeping. Writing a mark dissipates heat, erasing one costs energy. Landauer's principle quantifies the minimum toll. Removing one bit of information must release at least KTL and KT-2 of heat to the surroundings. Real devices pay more, but the logic is universal. Living systems meet the cost with metabolism. By consuming free energy and exporting entropy, cells maintain low entropy order. Proteins folded, gradients held, memories stabilized, within a high entropy environment. The brain spends a lavish share of the body's power budget to keep fragile patterns intact, refreshing them against molecular noise and decay. Memory is not magic. It is a physical state that resists forgetting long enough to be useful. In neurons, long-term potentiation strengthens synapses through cascades of biochemical change, altering receptor densities and local structure. New spines bud from dendrites. Networks replay patterns during sleep. Fleeting signals consolidate into durable traces. The price is paid in ATP, in blood flow, in careful ion pumping across membranes. Forgetting, too, has physics. Pruning connections and overwriting synaptic weights generate heat and molecular wear. Another reminder that even silence has a thermodynamic bill. On planetary scales, isotopes serve as timestamps. Zircon crystals shelter uranium and lead in lattices that shrug off disturbance, preserving clocks that tick across billions of years. The resulting dates sketch the emergence of continental crust and the presence of liquid water early in Earth's history. Coral skeletons accrete bands that capture sea surface temperatures and storm scars. Speleothems grow in caves, layer by layer, recording rainfall in their oxygen isotopes and trace elements. Each archive has biases and gaps, yet together they overlap and corroborate, like eyewitnesses whose stories interlock. In astrophysics, lensing delays and echoes create calendars written in light's travel time. A quasar, split into multiple images by a foreground galaxy, will flicker at different moments in each arc. Measuring those delays weighs the lensing mass and constrains the expansion rate. Supernovae caught in different lensed paths can reappear years apart, their second act predicted by geometry. Even the cosmic microwave background, nearly uniform, carries tiny anisotropies that archive acoustic waves from the primeval plasma, a fossilized sound field from an epoch before atoms. All these records point in the same temporal direction. Causes precede effects, not by decree, but by habit of accumulation. Ash follows fire, a ring follows a season, a spectral redshift follows a climb from gravity's well. Traces collect downstream of events because entropy rises. States with more microconfigurations outnumber the tidy ones that came before. Retrodiction, inferring past causes from present marks, works because the world writes to its media more readily than it unwrites them. The arrow of time becomes visible in this quiet accounting. It appears in the soot on a ceiling, in the widened tree ring after rain, in the cooled glow of a white dwarf, in the hydrogen line shifted by a galaxy's retreat. Each mark is local, partial, and perishable, yet across scales they add up to a biography. Matter remembers by being rearranged, and forgetting comes as diffusion, corrosion, and noise wear patterns down. Between the making and the erasing, a span opens where histories can be read and lives can be lived. Memory in matter is thus the interface between physics and narrative. From molecules to mountains to galaxies, durable patterns preserve the order of happenings. The universe does not keep a single archive. It keeps many, redundantly and imperfectly, each paying the thermodynamic cost of keeping time. In their accumulation, causality becomes legible, and the flow from earlier to later gains substance, not as a metaphysical current, but as an ever-thickening palimpsest of marks no wind can fully erase. Beneath the calm of planetary arcs and pendulum swings lies a finer tremor. At quantum scales, the world does not march. It shimmers. Outcomes are not etched in advance, but offered as amplitudes, complex numbers that add and cancel like ripples crossing on a pond. Where classical paths would choose a single route, quantum dynamics admits a chorus. In the path integral picture, every possible history contributes, their phases weaving interference that brightens some futures and dims others. Probability in this realm is not ignorance of hidden detail. It is born from the square of amplitude, the Born rules quiet arithmetic. A slit opened or closed changes the pattern not by pushing particles around, but by rewriting which alternatives are allowed to interfere. The strangeness has precision. Statistical predictions survive relentless tests, from single photon interferometers to superconducting qubits looping through finely tuned circuits. Time enters the formalism as a parameter guiding smooth, unitary evolution. The Schrödinger equation carries states forward with reversible grace. Yet measurements arrive as discrete landings on definite outcomes, clicks in a detector, dots on a screen, an apparent jump not present in the continuous equation. The pace itself can shape result. Observed incessantly, an unstable system hesitates to decay, the quantum Zeno effect turning attention into a kind of stasis. Between smooth evolution and sharp outcomes lies the environment. No system is perfectly alone. Stray photons, phonons, and fields brush against it, recording partial information. Decoherence spreads phase relations into the surroundings, suppressing interference between certain alternatives and selecting robust pointer states. What appears as collapse becomes, in open system language, the practical loss of coherence to countless unseen degrees of freedom. Facts once smeared turn crisp not by magic, but by entanglement with a world too large to reverse. Entanglement is the signature bond of this scale, stitching distant parts into single descriptions. Pairs prepared together can show correlations that violate Bell inequalities, a pattern impossible for any theory of pre-assigned local properties. Signals still respect light cones. No knob turned here can send a message there faster than light. The correlations are stronger than classical, yet disciplined, bounded by quantum rules and indifferent to schemes for superluminal talk. Open systems drift toward equilibrium under the gentle governance of master equations. In the Lindblad framework, coherence leaks at calculable rates. Temperatures and couplings set the timescales for forgetting. Out of these flows, an arrow of time emerges without decree. Decoherence and dilution convert crisp phase relations into heat. Records accumulate in the environment. Erasure has a thermodynamic cost. Microscopic laws remain largely time-symmetric, but typical states evolve toward the many over the few, entropy's preference written in Hilbert space. There are formalisms where time itself is relational rather than imposed. In the Page-Wouters construction, a composite state can be timeless as a whole, while subsystems serve as clocks, their correlations defining before and after. In the thermal time hypothesis, a state determines its own notion of flow through a mathematical generator, tying tempo to information rather than to an external parameter. These approaches do not rewrite experiments. They suggest that temporal order may arise from correlations and boundary conditions, not from an absolute cosmic metronome. Bridges to the classical world span this terrain. The Ehrenfest theorem shows that quantum averages can follow Newton-like motion when states are narrow. UKB methods recover rays and trajectories where phases vary slowly. Decoherence prunes interference so that macroscopic objects trace stable paths. Continuity, so familiar at large scales, is composed from countless quantum intervals, much as a fluid smooth surface emerges from molecules in ceaseless motion. At the margins of current knowledge, Planck's scales mark a frontier rather than a minimum tick. There, quantum theory and gravity both demand a say, and the grammar is still being drafted. Yet within tested domains, the rules hold with crystalline reliability. Indeterminacy is not chaos, but syntax. Superposition, interference, and entanglement are its parts of speech. From their interplay, classical stories are written, one definite outcome, then another, while underneath, amplitudes continue their silent negotiations, composing continuity moment by moment. Life carries a pocket of time, beating within cells and organs like quiet metronomes. In a world where daylight slides across the sky and temperature ebbs and flows, organisms carve out their own cadence, translating cycles of light and darkness into chemistry, electricity, and behavior. At the center of this orchestration lies a master pacemaker, a paired cluster of neurons in the hypothalamus called the suprachiasmatic nucleus. It keeps near 24-hour time through molecular feedback loops. Genes such as PER and CAR-Y rise and fall in expression, their proteins returning to inhibit their own production and hours later releasing the brake. This transcription-translation cycle creates a self-sustained oscillation. Around it, thousands of peripheral clocks in liver, heart, lung, skin, and even immune cells tick to their own versions of the same script, coordinated but not identical. Light sets the phase. Specialized retinal cells containing melanopsin, intrinsically photosensitive ganglion cells, send signals directly to the suprachiasmatic nucleus. Blue-rich photons near 480 nanometers are especially persuasive, shifting the clock earlier with morning exposure and delaying it with light late at night. The result is entrainment, an internal rhythm synchronized to the external day. When schedules or travel misalign the two, jet lag emerges, mood dulled, sleep fragmented, until light, darkness, and routine coax the oscillators back into harmony. Hormones carry the clock's instructions through the body. Melatonin rises in darkness, whispering that night has arrived, while cortisol peaks near waking, priming metabolism and alertness. Core body temperature drifts with the day, typically dipping by about a degree near dawn and rising toward evening. These waves are not decorations. They gate when food is best processed, when muscles perform, when memory consolidates, and when the immune system patrols most effectively. Beneath the daily cycle, other tempos interleave. The heart's sinoatrial node fires with its own pacemaking currents, an electrochemical rhythm steered by the autonomic nervous system and metabolic demand. Lungs breathe in ultradian patterns, neurons chatter in oscillations from slow delta to quick gamma, and endocrine systems trace longer arcs. Menstrual cycles, seasonal breeding, migration. Development itself is timed. Somate clocks tick during embryogenesis, carving vertebrae with remarkable regularity. Molecular gears keep the beat with exquisite resilience. Circadian oscillators show temperature compensation. Rates of the underlying biochemistry change with heat, yet the period stays near a day. This stability is not costless. Maintaining gradients, resetting ion channels, transcribing and degrading proteins, all consume energy. Metabolism pays the fee so that ordered rhythms can persist within a disorderly environment, exporting entropy to keep the internal score. Feeding, fasting, and activity feed back on the clocks. A late meal can shift the liver's schedule independent of the brain, altering glucose handling and lipid metabolism. Exercise in the afternoon can nudge skeletal muscle clocks and improve sleep that night. Chronic misalignment, shift work, irregular meals, irregular light can push subsystems out of step, blunting hormonal peaks, disturbing appetite, and increasing risk for metabolic and cardiovascular disease. Perceived duration is a construction built atop these physiological tides. Under fear, time seems to dilate as attention sharpens and memory sampling densifies. During flow, minutes compress as prediction and action align. Dopamine modulates internal interval timing, stretching or shrinking subjective seconds, while aging broadens the ticks. Circadian amplitude diminishes. Chronotypes drift later in adolescence, then often advance in older adulthood. The sense of how long depends on arousal, novelty, and context, as much as on the clock on the wall. Sleep weaves the daily ledger into permanence. Slow waves sweep across cortex, spindles spark in thalamus, and synapses recalibrate. Memories stabilize as some connections strengthen and others soften. The glymphatic system pulses cerebrospinal fluid through perivascular channels more vigorously during deep sleep, clearing metabolic byproducts. These nightly housekeeping tasks unfold on a schedule set by both circadian timing and sleep pressure from wakefulness, with adenosine accumulating as hours pass and receding after rest. Even at fine scales, noise challenges precision. Thermal fluctuations jitter reaction rates. Stochastic gene expression threatens regularity. Biological clocks answer with network design. Coupled oscillators, redundant loops, and delayed negative feedback that smooths randomness into reliable cycles. Populations of pacemaker neurons synchronize through synaptic and diffusible cues, turning many imperfect clocks into one robust signal. Technology now listens closely enough to map these rhythms in everyday life. Wearables estimate phases from temperature, heart rate variability, and activity. Dim, warm evening light protects melatonin. Bright morning light and regular meals anchor the day. In medicine, dosing aligns with chronopharmacology to match drug action to biological windows, improving efficacy and reducing side effects. In performance, training shifts toward the hours when muscles and lungs naturally crest. All of these tempos remain tethered to physics. A photon is a message. Its arrival resets molecular gears. Ion pumps move charges across membranes against gradients, spending ATP to preserve excitable cells. Heat diffuses, imposing noise, while the geometry of vessels and tissue shapes delays and flows. Biology stands as a small island of measured rhythm contoured by universal laws, translating sunrise and sunset into chemistry, translating chemistry into thought and behavior. Thus the body becomes a conservatory of time, where multiple instruments keep overlapping measures, some fast and bright, some slow and deep. The melody is not metronomic. It flexes with season and age, with food and motion, with light and darkness. Yet through the din of change, the composition holds. Life keeps time, and in keeping it, finds a way to endure, anticipate, repair, and remember. From shadows on stone and sand slipping through glass to cesium in sealed tubes, the measure of time has tightened from seasons to seconds to subtleties beyond intuition. Ancient gnomons watched the sun. Water clocks bled minutes. Pendulums brought regular sway. Quartz crystals hummed an electrical rhythm. Then atoms took the role of metronome, offering transitions that neither fatigue nor weather can sway. The modern second is defined by cesium-133. Exactly 9,192,631,770 oscillations of the hyperfine transition in its ground state. In atomic fountains, cesium atoms are cooled, tossed upward, and interrogated as they drift through microwave fields. Feedback locks the microwave to the atom's preference. The result is a tick, so, even that if it drifted a second, the error would arrive after millions of years. Optical clocks climb to higher frequencies, trading microwaves for visible light. Strontium in optical lattices, ytterbium and aluminum in single-ion traps. Each references a narrow optical line stabilized by ultra-stable cavities. Frequency combs bridge optical ticks to radio counters, making the fast countable. Fractional uncertainties near 10 to the minus 18 turn height into time. A clock raised a centimeter runs measurably faster. No single device keeps civil time. Coordinated universal time is an ensemble average of hundreds of atomic clocks linked by satellite transfer and increasingly optical fiber. International Atomic Time, TAI, flows without leap seconds. UTC adds them to stay near Earth rotation, whose winds and tides refuse perfect regularity. Laboratories compare strontium to cesium, building a bridge toward redefining the second in optical light. Navigation depends on synchronized ticks. GPS, Galileo, GLONASS, and Beidou satellites broadcast stamped timestamps from orbits where gravity is weaker and motion is swift. Relativity is not a correction, but the operating principle. Altitude speeds the onboard clocks, velocity slows them, and both effects are pre-compensated, so receivers can trilaterate position to meters or better. A handful of nanoseconds becomes a map. Timekeeping has become geodesy. Portable optical clocks and fiber-linked comparisons sense gravitational potential. Lift a clock and it hurries. Lower it and it lingers. Networks of such instruments can contour the geoid, track groundwater changes, and monitor volcano inflation, reading Earth's shape in the pace of time. Chronometric surveying turns seconds into elevation. Clocks also interrogate nature's foundations. Long campaigns compare different atomic species to test whether constants, like the fine structure constant, drift. Sidereal modulations probe Lorentz symmetry. Synchronized arrays listen for transients that could betray passing dark matter fields. Proposals even imagine clock interferometers for low-frequency gravitational waves, using time itself as an antenna stretched across continents. Thus, the craft of time becomes a mirror. Each improvement reflects laws more sharply. Electromagnetism in spectral lines, quantum mechanics in line widths, relativity in rate shifts. The devices that tally days and guide ships to harbor now weigh mountains, test symmetries, and search the dark. In their quiet counting, the universe describes itself, one disciplined oscillation at a time. Light is the oldest archivist, crossing expanses with pockets full of dates. Every photon departs carrying a temperature, a color, and a delay, and arrives as a stamped envelope from a particular place and hour of the universe. The first entries in that archive are faint and everywhere at once. The cosmic microwave background, a near-perfect glow laid down when the young cosmos became transparent. Its temperature is just 2.725 Kelvin, yet tiny ripples, only tens of microkelvin, sketch the scale of primordial sound waves in the hot plasma. Peaks and troughs in that pattern reveal the amounts of ordinary matter, dark matter, and radiation, while polarization swirls, add notes about rionization, and the way gravity has tugged on those photons since. A single sky becomes a ledger of contents, age, and geometry. As space expanded and cooled, later pages were written in starlight. Spectral lines act as barcodes, thin dark notches from hydrogen, oxygen, calcium, and more. Stretch those lines redward, and the cosmic scale factor is revealed. The farther the shift, the longer the journey, and the younger the universe when the light left. Hubble-Lemaitre expansion emerges from these displacements, and baryon acoustic oscillations leave a preferred spacing in galaxy surveys, the fossil ring of early universe sound now frozen into large-scale structure. Some sources carry clocks of their own. Type Ia supernovae brighten and fade in a characteristic way. Calibrate that curve nearby and it becomes a standard candle far away. Their combined story showed that expansion is not merely continuing, but accelerating, as if pushed by a pressure woven into spacetime. Quasars split by gravitational lenses add another timing trick. Multiple images flicker with measurable delays, and those offsets weigh the lens and test cosmic distances with seconds as rulers. Between sources and eyes lies matter that edits the message. Intervening gas paints forests of absorption lines, with hydrogen's Lyman alpha series tracing the density and temperature of the intergalactic medium across epochs. Dust dims and reddens, its grain sizes encoded in the curve of extinction and in the subtle 2175 angstrom bump. Galaxy clusters imprint the Sunyaev-Zeldovich effect on the microwave background, slightly shifting photon energies as they pass through hot plasma, faint smudges that double as thermometers and signpost to mass. Closer to home, atmosphere turns stars into trembling points. Twinkle is turbulence made visible. Pockets of air with changing density bend wavefronts into moving speckles. Lift a telescope above the air, and steadiness returns. With it comes transit timing to the second. When a planet crosses its star, the dip in light reveals radius. The cadence and variations reveal additional companions. Spectra during transit whisper about atmospheres. Sodium, water vapor, hazes, etched as fine changes in color across the eclipse. Not all fossils are bright. Surface brightness dimming scales steeply with distance, making ancient galaxies appear ghostly even when intrinsically luminous. Yet long exposures gather their photons, building mosaics of the early universe where disks are clumpy, star formation is fierce, and mergers frequent. Infrared views add the hidden half. Dust-enshrouded starbursts, glowing in wavelengths stretched beyond the visible, assembling heavy elements behind veils that only cool light can penetrate. Time itself is recorded in arrival. A solar flare's X-rays, a supernova's optical flash, a gamma-ray burst's brief glare. Each is a dated telegram. Dispersion in plasma delays radio waves by frequency, turning fast radio bursts into probes of the electrons that fill intergalactic space. In lensed systems, the same event can replay years later in a mirrored arc, a cosmic echo predicted by geometry alone. Laboratories on Earth anchor this reading. Calibration lamps and frequency combs keep spectrographs honest. Atomic clocks timestamp photons to nanoseconds. Synchronized observatories catch the same transient from different longitudes. With these tools, light becomes both messenger and meter, cross-checked against standards, so that faint shifts translate into distances, masses, temperatures, and ages. Piece by piece, the timeline grows continuous. The microwave background fixes the first clear epoch. The Lyman alpha forest threads through the dark ages. Rionization lights the page with the first stars. Supernovae and lenses pace expansion. Galaxies and clusters trace the web's maturation. Each entry is partial, but together they intertwine into a narrative that runs from the universe's early glow to the present sky. In that narrative, photons are fossils not because they are old, but because they preserve conditions of departure with stubborn fidelity. Wavelength, polarization, angle, and delay are chisels marks on a durable record. Read carefully. The record yields a chronology without a master clock, only countless dated messengers, arriving from every direction, and a patient practice of listening to what color and timing have been trying to say all along. Stones keep quiet ledgers, and Earth turns the pages with patience. In crystals and layers, time is tallied without haste. Atoms rearrange, sediments settle, ice compacts, and each process writes a date in a script of isotopes, textures, and trapped traces. The record is not a single book, but a library, igneous, sedimentary, and metamorphic volumes, cross-referencing one another, until a chronology emerges that stretches from fire to flood, from mountain root to coral rim. Radiometric clocks provide the page numbers. Unstable parents decay into stable daughters at known rates, and their ratios become measures of duration. Uranium splitting into lead times the oldest rocks. Potassium becoming argon dates lavas and ash. Carbon turning to nitrogen through radiocarbon marks recent centuries and millennia. Argon-argon refinements, uranium-thorium series, and samarium-neodymium clocks extend the toolkit. Each method carries assumptions, closure temperatures, initial conditions, that geologists test by comparing independent lines until a consistent timeline holds. Among the most eloquent timekeepers are zircons, stubborn, durable, and fond of uranium. These tiny crystals outlast the rocks that host them, surviving erosion and metamorphism to be reused in younger sediments. Some detrital zircons from ancient sands carry ages beyond 4.3 billion years, and their oxygen isotopes hint at interaction with liquid water while Earth's surface was still cooling. Inclusions of quartz and mineral thermometers written within them add context. Temperatures, pressures, and the chemistry of the crust that cradled early oceans and continents. Volcanic rocks recount bursts and pulses. Basalts pour from fissures and plume-fed provinces, their cooling glasses locking in potassium that will one day reveal eruption dates. Ash layers fall, like time-stamped pages across vast regions, creating isochrons that synchronize distant basins. Tephrochronology links peatlands, lake beds, and marine cores by shared shards of volcanic glass, Letting climate records stitched on different continents share the same margins and numbered lines, ice keeps an airy autobiography. Snowflakes trap bubbles of the atmosphere. Compression turns snowfall into firn and then crystal, preserving ancient air in tiny ampules. Ratios of heavy to light oxygen and hydrogen isotopes in the ice track temperature at the time of deposition, while the gases within recount concentrations of carbon dioxide and methane, volcanic sulfates, and even traces of cosmic events. Annual layers, varves in frozen form, can be counted like tree rings, tying greenhouse swings, abrupt warming events, and quiet centuries into continuous sequences. Sediments translate the slow into legible rhythm. In lakes, light and dark laminations mark spring floods and winter calms. On ocean floors, foraminifera build shells that inherit the isotopic fingerprint of the water they grew in. Changes in species and chemistry, stacked one above the other, narrate glacial cycles and monsoon shifts. Lush plains store winds work. Speleothems in caves accrete drip by drip, their uranium series ages and trace elements recording rainfall histories. Coral skeletons track sea surface temperatures and storm scars in bands as regular as a metronome. Plate tectonics turns the planet's grand pages. New crust forms at ridges, documented by magnetic stripes that flip with geomagnetic reversals. Old crust sinks at trenches, erasing earlier lines but leaving structural echoes in mountain belts. Orogenies fold and fault, stacking slabs of time. Unconformities cut across chapters, signaling intervals of erosion or non-deposition. Supercontinents gather and separate, Rodinia, Gondwana, Pangaea, shifting ocean currents, climate belts, and the theatres where life diversifies. Life writes in parallel inks. Microbial mats build stromatolites, layering calcium carbonate into domes that capture early metabolisms. Cambrian sands carry the sudden multiplicity of body plans. Shells in limestone and pollen in peat shift with climate and habitat. Carbon isotope excursions register upheavals in the global carbon cycle. Mass extinctions punctuate the narrative with ash and shocked minerals, from the end Permian's flood basalts to the Chicxulub impact's iridium-rich boundary. Each biological note is dated by the stones it rests within and, in turn, helps calibrate the stone's own stories. Astronomical rhythms leave fingerprints in rock. Milankovitch cycles, precession, obliquity, and eccentricity modulate sunlight over tens to hundreds of thousands of years, imprinting periodicities in sediments and ice. Spectral analysis of layered records pulls these beats into view, allowing astrochronology to tune stratigraphic sequences with celestial precision. Magnetostratigraphy adds a barcode of polarity reversals. Together they bridge gaps where radiometric markers are scarce, aligning basins separated by oceans into a coherent score. Deep time aligns with deeper context. The sun brightens slowly across eons, nudging climate against a backdrop of greenhouse gases and continental geometry. Oxygen rose in the Great Oxidation, painting iron-rich seas and enabling complex life. Snowball intervals advanced and retreated. Tropical forests waxed and waned with mountain uplift and monsoon breath. Through it all, stones keep count, while oceans and air translate energy into weathered forms, and biology adapts, flourishes, and yields. Even the abrupt finds its place. Impact craters stamp punctuation, the Sudbury and Vredefort scars for deep chapters, Chicxulub for a sudden turn of plot. Flood basalts paint pages black, ash darkens skies and lithifies into widespread markers. River terraces step down as landscapes adjust to uplift and sea level change. Glacial moraines trace the edges of vanished ice. These fast notes sit within slow staves, giving the composition both rhythm and refrain. The reliability of the chronicle rests on convergence. Independent clocks and proxies, decay chains, magnetic flips, orbital beats, species turnovers arrive at the same dates when the interpretation is sound. Where they disagree, the discord becomes a question, and questions refine methods until harmony returns. In this way, geology's timeline is not asserted but assembled, its confidence growing with each cross-check and newly read core. Deep time speaks in slow syllables, but the language is precise. Crystals, layers, bubbles, and bands translate heat and light, pressure and chemistry into durable marks. Read together, they link Earth's biography to cosmic pacing, a warming star, a spinning, wobbling orbit, continents in motion and life braiding itself into stone. The books are heavy and quiet, yet their pages rustle with ages. In their margins the planet remembers. At the universe's steepest places, time thins to a filament and light learns to hesitate. Gravity there is not a pull, but a shape so abrupt that world lines kink toward darkness, and the ordinary pace of moments slackens into a drawn-out hush. These districts, where matter is packed to its limit and geometry folds in on itself, mark the edges of night. A black hole begins with a boundary, the event horizon, beyond which paths lead only inward. To a distant observer, clocks carried toward that boundary appear to slow, their signals reddening, their cadence stretching until they fade into silence. Locally, the passage is swift. Proper time remains loyal to the traveller, but separation of viewpoints reveals how curved space-time sculpts duration. Just outside the horizon sits the photon sphere, where light can orbit in a precarious loop. Farther out, gas in the innermost stable circular orbit rounds the abyss, blazes in X-rays and imprints, reflections that sketch the depth of the well. Spinning holes drag space-time itself, the lens-thirring twist, carving an ergosphere where nothing can remain still relative to the distant stars. Light does not escape untouched. Gravitational lensing by a hole or a compact cluster bends beams into arcs, rings, and a faint ladder of photon rings that circle the shadow. The size of that dark core, imaged around M87 star and Sagittarius A star, matches the predictions of curvature alone. Even without a camera, timing tells the story. Signals that skirt a deep potential arrive late by the Shapiro delay. Echoes from accretion disks beat at frequencies tied to orbital radii. Flares shear and cool on clocks set by gravity. Neutron stars test the slope in a different key. A mass comparable to the Sun is compressed into a sphere the scale of a city, its interior a lattice of neutrons, or something stranger, stiffened by quantum pressure. Space-time curls so tightly that photons leaving the surface lose energy, shifting to redder colors. Light bending is so severe that more than half the crust is visible at once. Pulsars born from these remnants turn like meticulous beacons, sweeping radio or X-ray beams across the sky with sub-microsecond regularity. Their pulse trains cross interstellar space and, as they graze gravitational wells, accumulate delays that weigh companions and map geometry in units of time. In binaries, compact objects conduct a slower music of loss. The Hulse-Taylor pulsar's orbit shrinks at a rate that matches energy carried away by gravitational radiation, a confirmation written in decades of timing residuals. When two black holes spiral together, their waves rise in pitch and amplitude, the classic chirp, before merging and ringing down in quasi-normal modes that identify the remnant's mass and spin as surely as a struck bell names its alloy. The speed and polarization of those waves agree with general relativity to exquisite precision, fixing the propagation at light speed and leaving little room for alternatives. Neutron star mergers add light to the soundtrack. The coalescence that produced GW170817 arrived with a short gamma-ray burst and a kilonova that bloomed through optical and infrared bands as freshly made heavy elements decayed. Spectra traced R-processed nuclear synthesis, revealing where gold, platinum, and rare earths are forged, not in calm stars, but in collisions at the frontier of gravity's reach. Time delays between gravitational waves and photons set bounds on how both messengers cross cosmic distance. Their joint arrival turned space-time into a calibrated yardstick. Edges sharpen theory. Frame dragging is sensed near spinning holes. Innermost orbits are located by quasi-periodic oscillations. X-ray reflection spectroscopy and pulse profile modeling with missions like NICER pin down mass-radius pairs, squeezing the equation of state of ultra-dense matter. Tests of the no-hair theorem listen to ring-down harmonics. Pulsar timing arrays hunt for a background hum from supermassive black hole pairs. Strong field lensing counts the orbits of light itself. Each measurement is a conversation with geometry, translated into delays, shifts, and beats. The common thread across these extremes is the choreography of time. Deep potentials dilate rates, rapid motion trims intervals, Horizons impose one-way boundaries that partition stories into before and inside. Photons and waves serve as patient couriers, carrying imprinted histories of the paths they took and the slopes they climbed. The result is almost sculptural, a relief map where duration puddles in wells, thins on ridges, and flows along channels carved by mass and momentum. In this austere landscape, intuition yields to measurement. Clocks anchored in neutron stars, delays etched in lensed arcs, and ringdowns heard in laser baselines all point to the same grammar. Matter tells spacetime how to curve. Spacetime tells matter how to move. Clocks tell the tale. At the edges of night, that tale is clearest, stretched, reddened, echoed, and in those distortions, the laws that govern gentler places stand revealed with unusual clarity. Forecasts can be written for epochs as easily as for afternoons. The cosmos has its own barometers and fronts, expansion as a prevailing wind, gravity as a pressure gradient, radiation as a passing squall. On this largest canvas, tomorrow's weather stretches beyond calendars, and the atmosphere in question is space-time itself, thinning, cooling, and widening as ages pass. Acceleration is the first headline. Observations of distant supernovae, the cosmic microwave background and large-scale structure point to a universe whose expansion is speeding up, as if urged by a uniform, negative pressure component nicknamed dark energy. With that push, distances grow faster than light can bridge them. Galaxies not bound by local gravity recede beyond mutual reach, and the sphere of events that can ever exchange light contracts to an island of neighbors. Gravity holds small archipelagos together. The tide carries the rest away. Skies will change accordingly. Over tens of billions of years, the local group, Milky Way, Andromeda, and companions, coalesces into a single massive elliptical. Beyond it, other galaxies dim and vanish past the cosmic event horizon, their light redshifted into wavelengths so long that detectors must be measured in kilometers to notice the faintest whisper. The microwave background slides to colder colors, its temperature asymptotically approaching the de Sitter chill set by dark energy's horizon. Future astronomers, if any remain, will see a lonelier firmament and infer a smaller story unless their records remember a broader one. Stars keep their own extended forecast. Massive blue giants burn hot and fast, living for only millions of years before collapsing into neutron stars or black holes. Sun-like stars endure for billions, swelling into red giants and shedding planetary nebulae before settling as white dwarfs. The smallest red dwarfs, miserly with fuel and fully convective, can sip hydrogen for trillions of years. Star formation already declines as gas is locked into long-lived dwarfs and stellar winds and supernova heat and disperse what remains. The luminous era, abundant with fresh stars, gives way to a slower age lit by embers. Remnants inherit the night. White dwarfs cool and crystallize, their carbon-oxygen interiors forming vast diamond-like lattices. As heat leaks away, their spectra slide to infrared and beyond, dropping below detectability until only theoretical black dwarfs remain, cold, dark spheres that still carry mass and memory. Neutron stars spin down as magnetic braking turns rotation into radiation. Pulsars fall silent when their beams no longer cross space with sufficient energy. Black holes grow by mergers and accretion, anchoring the centers of merged galaxies, while scattering stars and planets in gravitational encounters. Dynamics continue even as fuel wanes. In the merged elliptical that replaces the local group spirals, close passages and resonances reshape orbits. Planetary systems suffer long-term instabilities. Some worlds fall inward, others are ejected to drift between stars. Stellar interactions feed central black holes, and the rare remaining mergers of compact remnants send faint gravitational waves through widening emptiness, the deep bass of cosmic music continuing long after the bright instruments have quieted. The long forecast depends on ingredients still being weighed. If dark energy is a true cosmological constant, a fixed energy of the vacuum, expansion coasts toward a steady exponential rate. If its equation of state differs slightly from -1, gentle evolution may await. If it dips below -1 into phantom values, Distances would grow so violently that gravity, galaxies, solar systems, and even atoms could be unbound in a far future Big Rip. Alternatively, dark energy might slowly decay or morph, easing expansion or ending acceleration. Each scenario writes a different destiny in the margins of the same equations. Speculative chapters linger at the edges. If protons are unstable, as some grand unified theories allow, baryonic matter would gradually fade, with lifetimes potentially around 10 to the 34th years or longer. False vacuum decay, if our vacuum is metastable, could in principle nucleate a bubble that rewrites the laws locally at light speed, ending chemistry and structure without warning. These possibilities remain unconfirmed. They are sketched to remind that the recipe is not fully known and that tomorrow's weather inherits the uncertainties of today's physics. Black holes dominate the far horizon. They are not eternal in a quantum universe. Hawking radiation gives them a temperature, tiny for the massive and inversely proportional to mass, while the background is warmer than a hole. Accretion and the ambient bath outpace evaporation. As expansion carries background light to colder colors, a crossover comes. The universe cools below a black hole's temperature, and evaporation proceeds. Stellar mass holes take stupendous spans. Supermassive ones require around 10 to the power of 100 years to finish, exhaling their mass into a drizzle of low-energy quanta punctuated by a brief final flare. The last fireworks of structure are dark and cold, but they are fireworks all the same. Beyond that, a quiet forecast. Heat death. Free energy dwindles as gradients flatten. No engine finds a temperature difference large enough to sustain work. Entropy approaches its maximum within the horizons allowed, and processes become rare fluctuations in a thin, steady bath. In a de Sitter-like future, the horizon itself carries a temperature and entropy, setting an ultimate background that cannot be further cooled. Time does not stop, but its stories do, replaced by a near featureless persistence. Yet alternate endings are penciled in the margins. Cyclic proposals imagine a bounce after expansion thins matter sufficiently. Emergent scenarios picture a prelude before what is now called the beginning. Evolving dark energy could resurrect structure or soften acceleration. Each possibility awaits sharper measurements of the cosmic expansion history, improved maps of large-scale structure, and laboratory tests of fundamental symmetries. Tomorrow's weather remains contingent on numbers with error bars. Clocks persist even as lights fade. Cooling curves of white dwarfs and neutron stars keep time across billions and trillions of years. Spin-down of pulsars, decay chains in the rare remaining isotopes, and the slow evaporation of black holes all mark intervals that dwarf human history. In these regimes, seconds are less relevant than exponentials. Patience becomes the natural unit. The forecast then spans from bright mornings of starbirth to grey afternoons of embers, from the present's accelerating breeze to horizons that seal islands of matter off from one another. It is written in equations that fit current skies and altered by parameters not yet pinned down. Between certainty and possibility, the narrative bends toward quiet. Degenerate remnants, sparse encounters, horizons that hum with faint thermality. Time's backdrop changes as the universe changes, weather determined by energies partly understood, measured by clocks that whisper long after calendars have nothing left to say. What if time is not a river, but a map, events spread like constellations on a silent chart, while the feeling of current is the mind's way of reading from point to point? In that picture, change is real, yet the flow is a rendering, an elegant interface layered over deeper structure. The laws sketch a tapestry, experience supplies the motion. Relativity offers the first hint. Space and time fuse into spacetime, where world lines trace histories and light cones fence off what can influence what. No, universal now slices the cosmos. Simultaneity depends on motion and gravity. Proper time, what a clock carries along its own path, is local and variable, dilated by speed and deepened wells. The stage is not a ticking auditorium, but a geometric arena in which intervals stretch and compress according to curvature and state of motion. Many fundamental equations run the same both ways. Newtonian mechanics, Maxwell's electromagnetism, and the core of general relativity are time-symmetric. Quantum dynamics evolves unitarily and reversibly between measurements. Even when nature shows a slight preference, subtle CP violation in weak interactions, CPT symmetry restores balance at the deepest level. If the rules do not single out a direction, whence comes the arrow? Thermodynamics answers with a boundary condition, not a decree. The early universe began in an extraordinarily low entropy state, smooth, hot, nearly uniform. From that special beginning, gradients formed, clumps grew, and accessible microstates multiplied. Entropy rose because overwhelmingly many more arrangements fit later than earlier. The Loschmidt paradox, why not reverse, meets coarse graining and statistics, while microscopic trajectories can, in principle, rewind. Typical macroscopic evolutions, given that initial smoothness, do not. The arrow then is not printed in the equations, but in the cosmic prologue. Records make the direction visible. Ash follows flame, tree rings follow seasons, spectra store velocities, neural patterns stabilize experience. Writing information dissipates heat, erasing it costs energy. Landauer's toll at KTLN 2 KT per bit. Decoherence spreads quantum phase into countless environmental degrees of freedom, turning superpositions into robust classical facts without violating the underlying symmetry. Each record is a scar of irreversibility, accumulating downstream of causes and seldom upstream. Story becomes possible because matter remembers. Some frameworks build time from correlations. In relational approaches, no external clock is needed. Subsystems serve as clocks for one another, and before and after arise from how states are entangled. The thermal time hypothesis goes further, deriving a flow from the statistical state itself. Given a distribution over possibilities, a preferred generator organizes evolution. In these views, tempo is not imposed from outside the tapestry. It is woven from the pattern of threads. Biology adds the felt contour. Brains integrate signals over windows, predict near futures, and edit near pasts. Dopamine nudges internal interval timing. Attention dilates or compresses perceived seconds. Hippocampal and entorhinal sequences lay out episodes along ordered routes. The present is a constructed span, a few hundred milliseconds stitched into a coherent moment, while post-dictive processes polish what just occurred. The sense of flow is consistent and useful, but it is a computation, not a fundamental force. Illusion, in this context, is not falsehood, it is appearance with rules. A rainbow is an optical computation that depends on angle, wavelength, and droplets. It vanishes if the geometry changes, yet it is law-abiding and measurable. So with time's flow, engines require gradients. Cooling irons do not spontaneously glow. Black holes redshift signals toward silence. Relativity still separates can from cannot with light cones. Gravity still makes clocks disagree. The mirage is disciplined by geometry and entropy. Clocks, then, are instruments that compare correlations. An atomic transition counts oscillations. A pulsar ticks in radio. A white dwarf cools along a predictable curve. Each functions because the world permits stable patterns and because the initial conditions set an arrow for them to travel along. The flow felt in consciousness rides atop this scaffold, stories assembled from records under thermodynamic constraint. If time is an illusion, it is the most constructive kind, a narrative layer that turns a static tapestry of relations into a lived sequence of moments. Stars still burn hydrogen to helium, galaxies still shear and merge, signals still arrive late from depths. Underneath, the laws remain serenely symmetric. Above, histories unfurl with direction, because a low entropy dawn gave them room to grow. Between symmetry and story lies emergence, an elegant mirage that guides planets, engines, and dreams, while the cosmos continues to keep its quiet geometric books.